Have you ever stopped to think about what actually happens when you open a website, send a message, or stream a video? It feels instant, almost effortless. But behind the scenes, there's a structured conversation happening between computers, and that conversation follows very specific rules. Those rules are called networking protocols. And at the center of all modern networking is something known as TCP/IP. Welcome to Bluehat Cybersec Academy. Today we're going to break down TCP/IP and networking basics in a way that feels clear, practical, and easy to follow, just like explaining it to someone sitting right next to you. In this session, we'll talk about what TCP/IP really is, how it compares to the OSI model, and finally, how data actually flows through a network step by step. So let's get started. To understand networking, we first need to understand what TCP/IP actually means. TCP/IP stands for Transmission Control Protocol and Internet Protocol. And one important thing to know right away is that TCP/IP isn't just one protocol. It's a collection of protocols that work together to make sure data can move from one device to another, reliably and efficiently. In simple terms, TCP/IP defines how data is created, how it's packaged, how it's sent, how it's routed, and how it's finally received and understood on the other side. Unlike purely theoretical models, TCP/IP is practical. It's not just something we study. It's what the internet actually runs on. TCP/IP is organized into 4 layers, and each layer has a very specific responsibility. Each one depends on the layer below it, and together they form a complete communication system. Think of it like a delivery process, writing the message, packing it safely, labeling it correctly, and finally delivering it through physical transport. Let's walk through these layers in order. Everything begins at the layer closest to us, the application layer. This is where user-facing applications operate. Web browsers, email clients, file transfer tools, all of them interact with the network through this layer. The application layer provides network services to applications, not directly to users, but to the software users rely on. Some of the most common protocols here include HTTP and HTTPS for browsing the web, FTP for file transfers, SMTP, POP3, and IMAP for email, and DNS for translating human-friendly domain names into IP addresses. When you type a website address into your browser and press enter, that request begins right here. Once the request is created, it moves down to the transport layer. This layer is responsible for end-to-end communication between devices. It decides how data should be broken up, how it should be transmitted, and how reliability should be handled. At this level, data is divided into smaller pieces so it can travel efficiently across the network. The transport layer also manages flow control and error handling. There are 2 major protocols here. TCP, or Transmission Control Protocol, is reliable and connection-oriented. It ensures all data arrives in order, and arrives without errors. UDP, or User Datagram Protocol, is faster and connectionless. It doesn't guarantee delivery, but it prioritizes speed. That's why web pages and file downloads rely on TCP, while video streaming, online gaming, and voice calls often use UDP. After the transport layer, data moves into the internet layer. This is where routing decisions are made. The internet layer determines where the data needs to go and how it should get there, even if it has to cross multiple networks along the way. This is where IP addresses play a critical role. Protocols like IPv4 and IPv6 handle logical addressing. ICMP supports error reporting and diagnostics, and ARP maps IP addresses to physical MAC addresses. In simple terms, this layer ensures data knows its destination and the path to reach it. At the bottom of the TCP/IP model is the network access layer. This layer really focuses on physical transmission. It handles how data is sent over the actual network medium, whether that's Ethernet cables, Wi-Fi, fiber optics, or wireless signals. It works closely with network interface cards, MAC addresses, and framing, converting data into electrical signals, radio waves, or light pulses. This is the point where data leaves your device and travels across the physical network. Before moving forward, it's important to talk about another model you'll hear about often, the OSI model. The OSI model is a 7-layer conceptual framework designed to help people understand how networking works. It's structured, detailed, and extremely useful for learning and troubleshooting. The 7 layers are application, presentation, session, transport, network, data link, and physical. Here's the key distinction. The OSI model is primarily a teaching model. TCP/IP is the model that's actually implemented in real networks. While OSI separates responsibilities into 7 distinct layers, TCP/IP simplifies things by combining layers. In TCP/IP, the application layer covers what OSI splits into application, presentation, and session. The network access layer covers what OSI separates into data link and physical. An easy way to remember this is simple. OSI explains how networking should work. TCP/IP shows how networking actually works. Now let's bring everything together with a real-world example. Imagine you're opening a website in your browser. You type a website address into the browser. The browser creates an HTTP request. Before that request can be sent, DNS translates the domain name into an IP address. The data moves to the transport layer. Here, it's broken into smaller chunks called segments. If TCP is used, port numbers and sequence numbers are added to ensure reliable delivery. In step 3, those segments are then wrapped inside IP packets. The source and destination IP addresses are added, and routers use this information to forward the packets toward their destination. Step 4. Network access layer. Physical transmission. Each packet is placed inside a frame. MAC addresses are attached, and the data is transmitted across the physical network, either wired or wireless. Receiving the data. The reverse journey. When the data reaches its destination, the process happens in reverse. Frames are removed, packets are processed, segments are reassembled, and the original data is delivered to the application. Adding headers as data moves down the layers is called encapsulation. Removing those headers as data moves back up is called decapsulation. Why understanding TCP/IP actually matters? When you step back and look at it all, TCP/IP isn't mysterious. It's a layered system where every component has a purpose, and every layer plays a role in making communication reliable, scalable, and efficient. Understanding these fundamentals opens the door to deeper topics like cybersecurity, cloud computing, network engineering, and DevOps. Once these basics click, everything else starts to feel far less intimidating. Thanks for watching Bluehat Cybersec Academy. If this video added value to your day, give it a like, share it with someone who could benefit, and subscribe for more content that breaks down complex networking and cybersecurity concepts into clear, practical understanding. Until next time, keep learning, stay curious, and we'll see you in the next session.